Alright, now we're going to get an introduction to the simplex method. It's called the table method for you to see what's going on and how some of the things are set up. In the last chapter we used x, y, and z, sometimes w, as our variables, but in this chapter we'll be using a matrix method called the simplex method. And it's used for problems with many variables, too many for us to graph. It is not convenient to use letters such as x, y, z. So instead, we're going to use x sub 1, x sub 2, x sub 3, and so forth and so on. But what's nice about these is whatever the coefficients are with these particular ones, that's the column that the numbers go in. Sort of cool. Standard maximization problems in standard form. Here is an example of that, and this is something that we had also in the last chapter. The objective function is being maximized. Our linear constraints are less than or equal to, and our variables have got to be positive. So still the same type of problem. So now slack variables. To change a linear programming problem to matrix methods, we have to remember some components about a matrix. In the simplex method, the constraints and the objective function are together in a matrix that looks like the following. It's called the initial tableau, similar to the Gauss-Jordan except for the final row. So don't worry about the final row. That'll come in the next section. But notice linear constraints with slack variables added. Remember, in a matrix, this vertical line represented equals. So in order to use the simplex method, we start by changing the constraints, which are linear inequalities, into linear equations. Now check this out. I haven't left this part yet. This side right here is less than or equal to 20. This second one is less than or equal to 16. So what a slack variable is we're going to be adding a non-negative variable to what they call pick up the slack. Whatever it takes to make this equal to 20. So let me keep on going down here. For instance, the linear inequality 5x sub 1 plus 3x sub 2 less than or equal 16 would change to 5x sub 1 plus 3x sub 2 plus s sub 1 equals 16. And the s sub 1 takes up any slack that's necessary to make this inequality equal to 16. A different slack variable must be used for each new constraint, okay, because how much is necessary to pick up the slack in one inequality may not necessarily be the same amount for the next one. So we have to use different slack variables. And also remember that all the slack variables must be greater than or equal to 0. Alright, next part. Basic solutions, basic feasible solutions. We call the system of inequalities of a linear programming problem an I system, I for inequality, and the associated system of linear equations obtained by adding slack variables an E system, E for equation. Solutions for the I system are the points in the feasible region. For example, from the last chapter handout, we had the following problem. Remember, this was my feasible region, and any corner on here was points on the feasible region. And we would come and list our corners and individually put them into our objective function. So in the last chapter we found that these last two corners were equal to, once we put them into the objective function, it's where my objective function was maximized. I had a tie. So now the solutions for the E system for this particular problem can be found easier by the use of a table where we don't have to graph. So for this problem we have the following equations correspond to linear inequalities. So a couple of things going on here. The x and y are changed to x sub 1, x sub 2. So for this first inequality we add s sub 1 equals 100. And for the second inequality, again changing the x to x sub 1 and the y to x sub 2, we're going to add s sub 2 to equal 200. And also remember, all these variables have got to be greater than or equal to 0. I'll be back to that in just a second. So now the table is going to be given. You're going to have to fill it out. So let's see what we can do. In my A solution here, x sub 1, x sub 2 are 0. So I go back up to these equations, that E system, and substitute it in. So for this one, if x sub 1 and x sub 2 are 0, then that would, in a sense, I don't have to account for those. That would be 0, so my S sub 1 would be 100. Let's see if that's what I put. So for the next part, S sub 2, remember X sub 1 and X sub 2 are 0. So if those are 0, my S sub 2 would be 200. So far, so good. Don't worry about this yet. I'll be back to that. So now when X sub 1 and S sub 1, now it gets a little bit more difficult, but not too bad. So if X sub 1 and S sub 1 are 0, right here I've got to use this first equation. So I end up with 3x sub 2 equals 100. So divide both sides by 3. My x sub 2 should be 100 over 3. So now that I know what x sub 2 is, I can go into the next equation. Remember, x sub 1 is 0, so that one drops out. So I need to go 4 times 100 over 3, 4 parentheses, 100 divided by 3. So now that's this side plus s sub 2. I need to subtract that from 200 minus, let me do my second answer. I'm going to go ahead and frac it. So my s sub 2, come on, there's my 200 over 3, excuse me. So now in C solution, x sub 1 is 0, s sub 2 is 0. So x sub 1 is 0, s sub 2 is 0, so that means I need to work with this one, because I want to try to find an equation that just has one variable. So I have 4x sub 2 equals 200. If I divide by 4, that should be 50. Very good. So now, let me go back up here, because x sub 1 is 0, so 3 times 50 would be 150. I need to subtract that from both sides, so s sub 1 should be a negative 50. Alright, let's go to D. X sub 1, oh, I need to find x sub 1. So x sub 2 and s sub 1 are 0. X sub 2 and s sub 1, that would be my first one. So I'd end up with a small equation, 2x sub 1 equal 100. If I divide by 2, x sub 1 should be 50. So now let me go to the bottom equation, because I have x sub 1. X sub 2 is 0, so this is out. So if x sub 1 is 50, 5 times 50 is 250. Subtract that from both sides. S sub 2 should be a negative 50. Alright. X sub 2 and s sub 2. X sub 2 and s sub 2. That's this one. So 5x sub 1 equals 200. Let's divide by 5. So that should give me 40. So we'll go plug 40 back in up here. If I put 40 in here, that would be 80. This is 0, so I've got 80 plus s sub 1 equals 100. So s sub 1 should be 20. Okay. Now this one is the difficult one, because if I put s sub 1 and s sub 2 is 0 in here, notice I've got two equations, two unknowns. And this is where I like to go to my matrix. Remember, this is what we did in the last chapter. I think I've already put it in just to save time. So go edit. Let's go put this in. So I've got 2, 3, 100, 5, 4, 200. So let's quit that. And I can use my matrix. Under math, remember RREF, that's row reduced echelon form of that matrix. Let's go frac it. Okay, so x sub 1 is 200 over 7. Let's go. And x sub 2 is 100 over 7. Okay. Now, feasible, guys, feasible means are the corners attached to the feasible region. For that to happen, all my variables, every single one of these have got to be positive. So the C solution and the D solution are not feasible. The rest of them are. And if you'll pause me just a second, go and see if these that are feasible do not well, let me see. Can I move this down just a smidgen? Yeah, just a smidgen. A corresponds to the first one. B corresponds to this one. E corresponds to this. Remember, all I see is x sub 1, x sub 2. And F corresponds to this one. So I'm going to put them in my objective function, and I should end up with the exact same thing that I've got up there. If it's a no, we can't put it in there, so we ignore it. So that is the table method. Not too bad. So you need to practice on this. In the next video, we actually have one that we can practice on. So go and try.